Alrighty, so as I indicated previously, tonight we'll have lecture for the first hour or so. You can see it's just the sun setting, and we need to wait about an hour after the sunset before we can really see things. And then we're going to go out to Holmes Lake and look at the sky for a short amount of time, just getting ourselves oriented in how that works. And so we'll probably head out there just a little after 9, and we should definitely be done by 10. I know the lab's supposed to go to 11, but we'll finish early. So, getting started with the lecture things. Y'all recognize this ball here, the Earth. And you might wonder, why did I start with the Earth for an astronomy class? Well, the Earth is the astronomical body that we know the best, right? Because it's the one we're on. And so a lot of what we do, we start from the Earth and we determine what we see on the Earth and compare it to other things. Now, the Earth is a planet. How many planets are there total? 8, right? And so, I know everybody knew that. I just making sure we...
9.
No?
Used to be 9.
Used to be 9. But Pluto never belonged. In fact, one of the things, remember I said they discovered that Pluto is actually larger than Eris, which as a consequence means the density of Pluto is less than they had thought it was before, which makes it less like, well, a planet. Okay, so the size of the Earth. The Earth is, we use kilometers for our scientific units, and so it has a radius of 6,371 kilometers in the normal units we would use, or 3,909 miles. You really won't see miles anywhere in science. It's just not something we use. But I have that there in parentheses, because it's something we're more familiar with. What's 3,909 miles away? Driving from here to California and back, Okay, it's actually, that would be a little bit farther away than the radius of the Earth. But, yeah, if I remember right, it's around 2,000 miles to get from here to California. I should know the first 2 years out here, I drove home every summer instead of flying home. The mass of the Earth is about 6 million or billion trillion metric tons. Well, that's a really big number, right? Billion trillion. We don't like to say things like billion trillion or trillion billion or anything like that. It sounds ridiculous. We also don't like to write numbers like this. Right, there's the actual value. 5, let's see now. We can count these. This would be hundreds, thousands, millions, billions, trillions, quadrillions, quintillions, then sextillions, and then septillions. So 5 septillions, 970 sextillions kilograms. That's, once again, it sounds pretty ridiculous, right? So instead, we use scientific notation. Scientific notation is really nice for a couple reasons. First and foremost is it's simple to write, and you can look right here and see how big the number is. Times 10 to the 27 means, so you take this and you multiply it by 1 followed by 27 zeros. And so I can just take this and I say, well, this is the rough size, and this is giving me, the exact value. So one of the things that you're going to have to be able to do and familiar with is how to use scientific notation. So I'm going to have a slide coming up on how to do it. I was going to show you here, and I was like, wait a minute, I should wait until I get to the slide that shows you how to do scientific notation before I actually show you that. We use the metric system in many ways because the metric system is more convenient. Everything's a factor of 10. We use things like centimeters, kilograms. We have these prefixes that are powers of 10. And I can always convert from things like, a milliliter to a liter. It's really simple. There are 1,000 milliliters in a liter. Whereas converting from, ounces to gallons, I really don't know. I think it's 128, but it might be different. That might be a half gallon. I don't know. Actually, that's probably cup. Clearly, I am lost when we talk about those types of measurements. The reason is they're complicated. Now a person can learn those complicated things, but we've got plenty of other complicated things to worry about. Why make our units something complicated? So we use the metric system and scientific notation to simplify our lives. Another reason why the scientific notation, I know it would be nice to have the example of scientific notation next, but I don't. Another reason why it's convenient is because it allows us to know which numbers are important. In that preceding number, this number here, I only have 3 digits in that number. Every digit in the number when you're using scientific notation is important. Any one that you didn't put in there is not important. So here I can see, oh, all of these zeros were unimportant. If the first 0 was important, I would have written 5.970 times 10 to the 27 kilograms. Do need to have the units. If you don't put the units, I don't know. Could be grams, could be slugs. Slugs is the English system, the system that uses pounds. Slugs is the unit of mass in that system. You've never heard that, right? Yeah. Okay. Next thing that we study in astronomy besides the Earth is the moon. Now, as we go through class, once we get started into astronomy, we're not going to start with these things. We're actually going to start with the history of astronomy and work forward through the tools they use, and then we'll get to stars, and after stars, we'll get to star systems. That's where we get to planets. So it's going to be a while until we actually get to planets. There are some books that will start with the Earth and Moon and work out, others that start out and work in. Okay, so the Moon is a satellite. That means that the Moon is orbiting around the Earth. Everybody knew that, right? Of course, ancient people thought that everything orbited around the Earth. They thought that we were the center of the universe. And then they decided, no, we're not the center of the universe. The sun's the center of the universe. And now they've changed it again. And I say they, it's long before we were born. And now they believe nothing's the center of the universe, that there is no center. So the understanding has changed quite a bit. But as you look out, the moon is the closest object we see. The moon is orbiting around the Earth. And if you were to go out right now, we will be in a little bit, you'll see the moon up in the sky. We have a waxing gibbous moon right now. Gibbous means that it's humpbacked or like a pregnant belly. So the moon right now looks kind of like that side's supposed to be circular and that side is kind of humpbacked. And so that's a waxing gibbous. And we'll learn all about those later on. I could have done a better job. Here, let me show you a better job. Because you got to know I can do a better job. First I go like that, then I erase half of it.
Nice.
Uh-oh. And then I screw up. Don't worry about that. I know. It's completely impressive. I'm such the artiste.
Wait, it's an A.
Not bad.
No, it's a lemon.
Okay, moving on. I'm artistically challenged. The moon is rocky, right? It doesn't have lakes, marshes, doesn't have an atmosphere. It's just a rock. Well, the Earth is a rock, Mars is a rock, Venus is a rock, Mercury is a rock. They're all rocks. The Earth has an atmosphere. Venus has much more. Mars has much less. Mercury has virtually none. But they're rocks. The moon's like them. In fact, the moon looks a lot like Mercury. If you look at the moon, you look at Mercury, you have to look carefully to see the differences. Mercury has things we call lobate scarps. It has these cliffs where part of the planet has slipped down. The moon doesn't have those. So that's something you can see that's different on the two, but they look a lot alike. The moon has a lot of craters created by meteors hitting it. On the Earth, do we have craters from meteors hitting the Earth?
Yeah.
We do. Now, I should probably be careful. The word meteor is actually for the light you see when it's going through the sky. It's a meteoroid before it comes into the atmosphere. It's a meteorite when it hits the Earth. And it's the meteor when you see that light in the sky. So technically, it's not a meteor impact. It's the meteorite that hit the Earth. At this point, who cares? Later on, we'll care. Okay, so we have who has actually seen a crater from a meteorite impact? Okay, we got a couple. Where did you see, Eliezer?
The Yucatan Peninsula.
Okay, I've never been there. Okay. I did for my anniversary 2 years ago go to Cozumel, but yeah, didn't see that. Where have you seen
I saw one in Minnesota.
Minnesota?
Yeah.
The one I've seen is the one out in Flagstaff, Arizona.
Yeah, I saw that one too.
He's been everywhere. I actually, after I started teaching astronomy, a student and I took a road trip out to Flagstaff from PUC. I figured it was, something to do with my time. Back before I was married, clearly. Otherwise, it would have been my wife. You understand. I took my wife there as we went to get married because it was that important to me. We took a road trip from here to California to get married. We actually also stopped in Santa Fe, New Mexico, to see an annular eclipse of the sun, which was totally cool.
Oh, wow.
And this is 2015, right?
Yes.
In 2 years, 2017, at the beginning of the school year, there will be a total eclipse of the sun that we're just off of the path of totality. If you go down to Nebraska City, that will be in the path of totality. So if you just go down to Nebraska City at the right time, it's like August 21 or something, 2017, you'll see a complete solar eclipse. And I was starting to plan, we're going to have a field trip. Problem is, it'll probably be like 3 days before school starts.
Oh.
Yeah.
How long do you need school to start?
I know, because I want to have a field trip. This is like an awesome field trip that you don't get to have, but once every long time.
Well, you could have all the freshmen going if you could.
Anyway, so the Earth does have some meteor impact craters, but nothing like you see on the moon. Why do you suppose there's a difference there?
There's no atmosphere on the moon. Well, there's not an atmosphere like here on the moon.
Yeah, we can say there's no atmosphere. There's virtually nothing. So there's no atmosphere. The atmosphere causes a lot of erosion. And so on the Earth, we have plenty of erosion. We have water, we have atmosphere. Our surface completely is remade all the time. But the moon doesn't have that, so it has old impact craters. The one in the Yucatan Peninsula is dated to be, I think it's 65 million years old. That's pretty old for Earth. It was also discovered about 15 years ago. Now, people have lived there for much longer than that. But it was discovered by people who were looking for mineral resource, or actually not mineral, for oil. They were looking for oil, and so they were doing some surveys of the ocean floor between Mexico and the United States, and they saw what looked like part of a ring. They studied it more carefully and discovered that it was the remnants of an impact crater, which goes up onto land as well. And so, it wasn't obvious. The one in Arizona is, I think, dated to be somewhere around 150,000 years ago. Not nearly as old, and thus far, far more obvious. Also being in Arizona, Arizona has a name that means dry area, right? So you have a lot less rain, a lot less water action causing the surface to change. Okay, continuing on, I'm going way, way slower than I intended. The moon is obviously much smaller than the Earth. I say obviously much smaller than the Earth. If you knew nothing, you would look at the moon and say, okay, the moon's that big in the sky. The Earth, I can't even see And so you would say, well, the Earth must be way, way bigger. But that wouldn't be conclusive. Because if you were standing on the moon, you would say, the Earth is, okay, it's going to be bigger. The Earth is like that big in the sky. But the moon is, covering everything. Right? You can't just take that perspective. You have to take into account how far away it is before you can determine the sizes. And we'll actually discover that the determination of the size of the moon was done long before Christ was on earth. And it was done very accurately. It's pretty surprising when you see that these people who we tend to think had no technology made some really creative and accurate measurements.
How did they do it?
Well,
I'm actually honest.
I'm trying to remember. The sun one was from shadows, and the moon, I think, was from timing the eclipse or something like that. We'll get there, and I'll remember when we get there. I remember it was done. Okay. Because the moon is really small, it should have cooled quickly. It's cold, has no life, as far as we know. So these are the most obvious things. We go out further, and we have a bunch of planets. And so here we have pictures of 4 planets. Ceres. Anybody know anything about Ceres?
Is that a dwarf planet?
It is indeed. It's an asteroid. It's in the asteroid belt, and it's classified as a dwarf planet. Oops. One of, I believe, 5 objects classified as dwarf planets. That was a new thing made up in like 2006 to appease people who thought Pluto should be a planet. Okay, then we have Jupiter, Saturn, Uranus, Neptune, Pluto, and Eris. How many people have heard of Eris? I did mention it in class yesterday. Eris is really the tipping point for kicking Pluto out. Eris was discovered, and their measurements said that Eris was bigger than Pluto. It's really bizarre that we have actually better measurements for the size of Eris than we did for Pluto until this summer. And this summer they discovered that Pluto actually is slightly bigger than Eris. And actually, when we get there, I'm going to do a lot on Pluto because we have all this new information that was really exciting. But both of these, Eris and Pluto, are also dwarf planets. But they're not asteroids. They are what we call Kuiper Belt objects. Many of the comets that we're familiar with are also Kuiper Belt objects. Pluto is the same type of thing as comets are. Now, if you look in these pictures, the scales of the top 5 are all the same. The scales of the bottom 6 are all the same. But the top scale and the bottom scale are not the same. The Earth is not nearly as big as Saturn. In fact, the Earth is much smaller than Uranus and Neptune. So this bottom picture has all of them to the same scale. And I have to zoom in for you to appreciate. So here is Earth right here. There's our size. Compared to Venus, we're slightly bigger than Venus. Venus is like 93% the radius of the Earth, so it's pretty close. Mars is only about 73%, so we're a fair amount bigger than Mars. Mercury's tiny here, but Jupiter is way bigger. And then you continue on, you have Saturn, which is also way bigger than the Earth. And these two here, Uranus and Neptune, are also far bigger than Earth. We tend to think of Uranus and Neptune as small, but if you compare them to Earth, they're bigger. In fact, all of these have a rock in the center that we believe is a bigger rock than the Earth. But they have gases outside of them, and that's what we see as the gas. So these are big, and then we have out here Eris and Pluto, which are, smaller than Mercury. So those are tiny little things. Here you had Ceres. You probably didn't notice that thing. Is it even?
Yeah.
Yes, it's there. Totally there. It takes up a total of 4 pixels. I mean, how could you miss it? Okay, so there's a fair range of sizes of the planets in our solar system. But that's just in our solar system. Now, we're going to learn about how these things got there, at least how we believe they got there. Now, let me once again say something I mentioned in the first lecture. The scientific viewpoint starts from there can be no miracles. It doesn't say there can't be a God, but it says everything we see has to have occurred naturally without a miracle. And so the scientific explanation for how these got here, we're going to learn that, but it precludes, it says there couldn't be a God. So it doesn't say there couldn't be God. It says God didn't do any of this. So if God did things, God could have made all these plants just the way they are, and science would never acknowledge that because they say, well, we don't have any miracles. We're not going to allow any miracles in our models. So when I talk about the scientific stories of how they came to be, that's how scientists have figured it out, starting from the premise of God didn't do it. And so I want you to learn the scientific ones. You don't have to adopt them as your own personal belief, but you need to understand why the scientists believe that. And part of it is understand that they start by saying, well, God didn't do it. So if God didn't do it, how was it done? Is their starting point. And I actually believe that God created the planets in the way science believes they came about. But that's my belief. Okay, first of our clicker questions for tonight. You didn't bring it?
I did bring it. Could we write it down on paper?
No, I won't count today either, but I will count tomorrow. So make sure you have a clicker by tomorrow.
What channel is this?
Channel 33. Which two objects in this list are larger than the Earth?
I know.
Yeah, I don't know. Good answer. It was on the preceding slide.
Oh, wow. Come on, yeah.
Oh, yes, and you have to put in A, B, C, D, enter. Of course, it's 2, so that was not the right choices. But
You want to write it down?
no, don't worry about it. Just think it in your head. Make sure you've chosen.
I know it.
So far, none of the 4 people who have answered have failed.
I would be sad.
And even though Laybirth just answered a second time, he's still right. It shows that you answered twice, but you were right both times. Okay, is it just the 4 people with clickers? I assume so. So our answers are... Whoops. No, I put those...
Okay, larger than here.
Okay. Yeah, that's right. For some reason, my brain said that was Saturn. I swear I'm going senile already. Because I was looking and I'm all, no, Saturn's bigger than the Earth. Uranus and Jupiter. Those gassy planets are all bigger than us. The rocky ones were the biggest of the rocky ones. So this is a rocky one, we're bigger. This is a rocky one, we're bigger. Eris is a dwarf planet. Clearly we're bigger than the ice balls. I say clearly we're bigger than the ice balls. Hey, maybe not. We are, though. Maybe it's not clear is what I mean by maybe not. Okay. The sun. The sun is technically the nearest star to us. Anytime I ask what's the nearest star, I am usually going to mean the nearest star to the sun. Right? The sun is our star. It's a star, like the stars you see up there in the sky. The sun is a pretty average star. It's in the mid-range for size and temperature. There's, as far as we know, there's nothing special about the sun. It's just our star. And so by studying the sun, we believe we can learn a lot more about the other stars out there. So the sun, compared to our planets, is huge. And it's a gas of... The sun is a massive incandescent gas. We'll learn that song. Gigantic nuclear furnace. We'll also probably learn the sun is a miasma of incandescent plasma. They might be giants. The first song they didn't write, but they did it. And then apparently they got some people with their knickers in a bunch saying, it's a gas that's ionized, and we call that a plasma. So they wrote a new version that sounds completely different. It's like a lounge lizard song. The sun is a miasma of incandescent plasma. Anyway, we'll get there. The sun's energy comes from nuclear fusion. That's what that poster in the back is all about. Nuclear fusion. There was a Nobel Prize that went to the people who figured out how the fusion could occur to make the sun produce its energy. So, I say produce its energy. It's converting mass into the energy we see coming from the sun. So it's a big nuclear bomb that continues to go off.
Yay.
Yes. And so the sun is the source of pretty much all the energy in the solar system. If you look at the Earth's energy budget, over 99% of our energy budget comes from the sun. The remaining energy in the Earth that doesn't come from the sun comes from radioactive decay of radioactive elements in the Earth. But it's less than 1% of our total energy budget. It's pretty much the sun is what drives us. It's like 100 times wider than the Earth and 300,000 times the mass of the Earth. So if you put the Earth, you can see over here, there's the size of the Earth compared to the sun. Yeah, huge. Jupiter is at least, you can make some kind of comparison. But the Earth is just itty bitty. And I think you could fit, I think it's something like 1 million Earths inside the sun. So, yeah. 100 cubed is, yeah. Did you have a question?
Yeah. Is that like a solar flare that's coming off the sun?
Yeah, this here is a prominence. When it snaps, it'll make a solar flare.
Okay.
Oh, so it's not a flare until it snaps.
Yeah. When it snaps, what you have is magnetic field lines that are coming. And I got to change colors. You ain't going to see jack with red on red. Green on red will work. You have magnetic field lines that are coming out like this.
Okay. Yeah.
And then these magnetic field, we think of magnetic fields like they're yarn. They're not really, but they do interact. And what will happen is this will merge somewhere down here, and that material out there gets ejected. And so you have suddenly lots of material that blows off. It actually makes shock waves, and you'll also have material that comes flying off over here from the recoil of that action.
Does that ever hit Earth or any of the planets?
It does. It does all the time. And when it does, you have cool things like northern lights visible in Lincoln. And you have things like this happened, what is it, somewhere about 17 years ago. There was a power plant in Canada that got knocked out because of the, when you have this occur, you have lots of charged particles, ions, that come flying toward the Earth. That's what makes the northern lights. But it also can cause problems with your satellites. And in this case that happened like 17 years ago, you had a surge in magnetic field that caused current to flow in a power plant enough to knock it out. So it can have some pretty dramatic effects on Earth.
But it doesn't burn us all up.
It does not incinerate us. Now, when the sun dies, it'll incinerate us, but we'll be in heaven. Actually, we believe that God will descend back to Earth after the millennium, and then we'd be on Earth, and, well, God will figure it out. Certainly not going to be my problem. Okay, the sun, according to science, is somewhere over 4 billion years. You'll see numbers between 4.6 to 5 billion years old. And it'll last about another 5 billion years. So it's about halfway through its lifetime. Billion years is a really big number. My mom would say, 6,000, get over it, And there's a big difference between 6,000 and 5 billion. That 5 billion, by scientific standards, is a fairly young star. Our sun, we believe the universe is about 13.8 billion years old, and other stars formed, lived, and died before our star was born. And so our star, the sun, actually has atoms in it that were formed from previous stars dying. The Earth has atoms in it that were formed from previous stars dying. In fact, anything on the Earth that's not hydrogen or helium came from a star that died before us. And so our age is relatively young, hence we have things like, iron, gold, that kind of stuff that you wouldn't have. The scientific theory is that the primordial material is all hydrogen and helium. And we'll learn that. We'll learn about that later. Yeah, I'm spending way too much time going in depth over things we're going to learn in another 3 months. So the solar system. We have things in the solar systems. We already talked about planets. We talked about the sun, the stars. We have asteroids, which you can see here, an asteroid belt that's between Mars and Jupiter. Lots of asteroids. Ceres is one of them. They're essentially broken up pieces of a planet, but not a planet that formed. In fact, if you take the total mass of all those asteroids, it's way less than the mass of any of our planets. So it was a developing planet, one that never grew large, and scientists believe it was either impacted by something or just the gravitational pull of Jupiter shredded it. So we have all these pieces out there in an asteroid belt. There are some other asteroids. For instance, there are asteroids that go in front of and behind Jupiter called the Trojan asteroids. And they just travel around with Jupiter, and they call them Trojan asteroids because it's something like the Trojan horse where you have them hiding. What was it?
I thought it was because they were trolling Jupiter.
Over here we are looking now zoomed out further, and actually I say zoomed out further. Let me zoom in on the picture so we can zoom in on the zoomed out picture. So here, the Sun, Mercury, Venus, Earth, and so on, the asteroid belt, and we just get to Jupiter's orbit. Come over to this one, and now you see Jupiter's way in here. Actually, Jupiter's there. And so it's zoomed way out so you can see other things, and you see the orbits of Uranus and Neptune. And yet, Uranus, you can pronounce it Uranus, you can pronounce it Uranus. I pronounce it Uranus to avoid the obvious jokes, but then somebody pointed out, well, Uranus doesn't really sound any better. Here we have the orbit of Pluto. Notice that Pluto sometimes is closer to the Sun than Neptune. Sometimes it's farther from the Sun than Neptune. And then we've got this big orbit here of Eris. And notice that Eris gets closer, well, you can't actually tell here, but Eris at its closest to the Sun is closer than Pluto at its farthest from the Sun. So Eris also will pass inside of Pluto. But Eris goes way out here, much farther away than anything else in the picture. Eris is this line here.
Oh, that's why I can't see it. Okay. The bottom. Okay.
There. That's my best.
Yeah, thanks. I didn't see it.
And notice that Eris's orbit looks nothing like a circle. The orbit of Pluto does not look like a circle either. If you look at doing the same color is not going to work. If you look at the orbit of Pluto, if you look at it by itself, it kind of looks, kind of looks like a circle. But if you compare it to the ones that are pretty close to circles, you can tell it's definitely not. Now, it is a lot smoother than my line. You all recognize that. So the orbits of the planets are not circles. That was something that wasn't discovered until somewhere around, that was 1600s or 1700s? Yeah, 1600s, I think. That the orbits are not circular. So it's a big solar system. We think the sun is incredibly far away. It takes like 8 minutes to get from the sun to us.
At the speed of light.
Yeah, because it's light. But compared to like Eris, the sun is super close. And that's in our solar system. We wouldn't use meters as a convenient way to measure the distance for these things. So we have a new unit, which I'm sure is on the next page, so I'm going to go to it and see. Yes, for once, I knew. We define a new unit called the astronomical unit, or AU for short. And the astronomical unit is defined as the average distance between the Earth and the Sun. That's probably the easiest test question that comes up. How far away is the Sun from the Earth? Answer, 1 astronomical unit, because that's the definition of the astronomical unit. Now, in meters or kilometers, 1 astronomical unit is right about 150 million kilometers. So we could do it in kilometers, but the astronomical unit is a lot more convenient. And here we see how far other planets are from the sun. And you see that Mercury, it has an average distance from the sun of just 4/10 of an astronomical unit. So Mercury's distance to the sun is 40% our distance from the sun. Mars is 1.5 astronomical units. It's 50% farther away from the sun than we are. Now, using a little logic, which gets the most intense solar radiation? Mercury, Earth, or Mars?
I'm going to say Mercury.
I'm going to say Mercury because it's so much closer. In fact, the solar radiation is proportional to 1 over the distance squared. So 1 over 0.4 squared compared to, for Earth, 1 over 1 squared. See, 0.4 squared would be 0.16. 1 over 0.16 is something like 8. So Mercury receives about 8 times as much solar radiation as we do. And it has no atmosphere to protect you. So if you were on Mercury and you stepped out into the sunlight, you would, of course, have severe sunburns almost instantly. Even on Mars, which is 1.5 astronomical units away, 1.5 squared is what, 2.25? And so you're receiving a little less than half the radiation from the Earth without the Earth's atmosphere. You would probably still have some problems because you'd have the ultraviolet light coming through. We have the ozone layer that helps to absorb some of that. Saturn, 10 astronomical units away. That means its solar radius is 1/100th of what we get. Far, far less. And Neptune, 30, of course, that would be 1/900th the radiation we get. So it's convenient to talk about how far a planet is from the sun using astronomical units. These numbers are all nice, simple numbers, no big zeros anywhere. So it's very useful in the solar system. The astronomical unit is not useful, though, when you talk about the nearest star. The nearest star is conveniently named Proxima Centauri. Proximal meaning proximal. It's the closest one. Centauri meaning it's in the constellation Centaurus. But Proxima Centauri is about 4.1 light years away, which means it takes 4.1 years for light to get from Proxima Centauri to us. Now, Proxima Centauri is like a brown dwarf or something. It puts out virtually no light. But if something were to happen to Proxima Centauri and it suddenly flared up in brightness, we would be seeing that over 4 years after it actually occurred because of the time it takes for the light to get to us. Okay. Our solar system, we believe, contains billions of stars. Our sun is just one of them. And those stars are virtually all you see when you go out and observe the sky. When we go out to observe the sky tonight, what we're going to be looking at is stars inside of our, I hope I've been saying galaxy here, not solar system. Our solar system contains one star. Stars in our galaxy. The only thing that you can see in the northern hemisphere that's not part of our galaxy is the Andromeda Galaxy. That's why the Andromeda Galaxy is one of the things you have to point out on your lab final, because it's the one thing we can see in the northern hemisphere that's outside of the Milky Way galaxy. And unfortunately, there's too much city lights to see the Andromeda Galaxy here, but we are going to one time take a trip out to Gary Walter's place out in the country. We'll choose a time when the moon is not up in the sky, and hopefully then we'll be able to actually see the Andromeda Galaxy instead of just know where it is and not being able to see it.
How do you know that will happen? I mean, when it's the right time, there's no moon.
Well, if the moon is waning, that is if you're past the full moon, then the moon doesn't rise until after sunset, and so it should be dark. If the moon's in the sky, then it's not dark. If the moon's not in the sky, then it's dark. So that's all I'm going to do is just make sure that we are on a waning moon, maybe a third quarter or something like that. Third quarter moon should rise about midnight. Well, we'll be done by then. Okay, so we're going to learn about stellar evolution, the life cycle, birth to death of stars. The astronomical unit, I said, is not very good for measuring long distances. We use the light year. 1 light year is, 10 10 trillion kilometers in 1 year is what it says here. And so the light year is easy to use. All you do to calculate a light year is you take the speed of light and multiply it by how long a year is. That's how you get a light year. And so it's a unit of distance, the distance light travels in a year. And so here we see what I was saying about Proxima Centauri being about 4.1 light years away. The universe contains lots of galaxies. And those galaxies are kind of clumped. So our galaxy, the Milky Way galaxy, is part of a small group of galaxies called the local group. But that local group is part of a bigger cluster of galaxies called the Virgo cluster. And that Virgo cluster is part of, a supercluster. And so we have these scaling. You start thinking about it, we have a solar system. Well, first we have the Earth, and we have the moon going around us. You go out further, you have the sun with all the planets going around it. You go out further, you have the Milky Way galaxy with all of the star systems going around it. You go out further, and you have the local group, which is a bunch of galaxies that are all orbiting around each other. You go out even further, you have the supercluster. It just keeps scaling out. The biggest thing known to man, I think they now have decided that the fairly recent discovery, maybe the last 3 or 4 years, the Great Attractor. The Great Attractor, there appears to be a drift of things going toward one region. And that's like the biggest thing. It used to be the Sloan Great Wall. But we're talking really large-sized structures when we start talking about big clusters of galaxies. And I swear I hit the button to go forward. So here we can see something to try to give us an idea of the scale of things. So here we have the local group, which looks small in this picture, and then it's expanded to get us, from one scale to another. Much better than that is a picture, no, I swear I've got things in weird order. I have a picture and a website I'm going to go to, and I thought it was next. But no. I'm going to summarize the units first. I'll probably do the how to use scientific notation first, and then I'll go back to it. I don't know what I was thinking when I organized these, but I was thinking, just not clearly. So here are units we're not going to use. I put them in here.
Why?
Why? Because it's convoluted. I mean, everybody probably knows they're 5,280 feet in a mile. But you probably never realized how they got to that. And here you can see how they got to that. There are 3 feet in a yard, 5.5 yards in a rod, 4 rods in a chain, 10 chains in a furlong, and 8 furlongs in a mile. So if you take these numbers right here, and you multiply those all together, it gives you the 5,280 feet in a mile. But it's pretty kind of stupid. Kind of pretty stupid? Stupid kind of pretty? Whereas over here, you can see everything's just multiplied by, tens. Much easier. And so the metric system, centimeter, the small measurement. We go much smaller. If we're going to talk about, light, we'll talk about nanometers. Nano means 1/billionth. If we're going to talk about things like atoms, we'll talk about femtometers. Femto means a millionth of a billionth. We that'd be a quadrillionth, right? Maybe. Yeah, let's not worry about it. Yeah. And then we go to large things. We could start talking about, if we wanted to, things like, petameters.
Gigameters.
That would be smaller, but yeah. We could talk about these crazy meter things, but in astronomy, we tend to shift off of the metric system when we go to the astronomical unit, the light year, and the parsec. So those are lengths that aren't part of the SI system. They're pretty unique. And here are some prefixes that are common that you should get to know. Notice I don't have peta in here. I stopped at giga. But you should know that giga means 10 to the 9th or billion. Mega means 10 to the 6th or million. Kilo means 10 to the third 1,000. Centi is 1 over 100. You know that there are 100 cents in a dollar? It's the same word. Centi is 1/100th. So there are 1/100th, 1/100, or 100 100ths in a 1. Then we have milli, which is 10 to the minus 3, micro 10 to the minus 6, and nano 10 to the minus 9. You should know those. You should be able to, on a test, say, what is milli? Milli is 10 to the minus 3. Question?
Excuse me, are these slides going to be online?
Absolutely.
All right.
As will the lecture. You can go listen to it again, because you know how interesting and riveting it is.
Do you put that earlier?
No, I put it up after. I put it up after. Now, I do have like last year's stuff up, and there's a lot of similarities, but because I'm making notations and whatnot, I put it up after so you have the notations.
Okay.
And when I work out problems, you'll have the worked out problems. Some important things to note. Everything over kilo, everything over kilo is capitalized. Kilo and below is lowercase. We have 3 M's, mega, milli, and micro. So the mega is capitalized, the milli is normal, and micro, we use a Greek M, which is a mu. I know that looks kind of like a U, but it's a Greek M. Trust me, I don't speak Greek, but I'm a physicist. Every time I do something that has lowercase Greek letters, I'm reminded my first year here at Union. I was talking about omega, and I wrote this. And afterward, a student who was being very polite and didn't want to embarrass me in front of the class said, I was in a sorority. We had to memorize the whole Greek alphabet. That's not the way you write an omega. I said, yes, this is the lowercase omega. And she's like, what? There's lowercase Greek letters? Because, the sorority system's pretty rigorous in there.
That's so boring.
But for the record, that's a capital omega and then a lowercase. So yeah, 2 different. Yep. Okay, so over here I have the scientific notation thing that I know logically would have come 20, 30 minutes ago. So here's an example of a number that when you read that, if you want to know how big it is, you have to sit down here and say, okay, so that's 1, 2, 3, 4, 5, 6 zeros, and then the 1. Scientific notation takes the counting out of it. What we do is we take this and we say, okay, I'm going to have to move the decimal place 1, 2, 3, 4, 5, 6, 7 to put the decimal right behind the first number. And so I'm going to multiply this by 10 to the minus 7. Minus 7 means this is a number smaller than 1. I had to move the decimal 7 places over to get to it. So this number here would just be 1 times 10 to the minus 7, which you can see I did not line this up there, but that's what it was supposed to be showing. I could really try to move that here. And I am always a man to take the challenge. Rectangle. Uh-oh. Got to be on the right layer. I have different layers so I won't screw things up, but I'm trying to screw it up here. Well, not screwed up. Trying to change it. It's not the right size. Okay.
We understand. Yeah, I do.
There. Just because you said I kind of made it worse, I changed it back.
Yay!
I'm glad I could make you happy. Okay, so the scientific notation works forward and backward. Let's try something like this. (2.57 times 10 raised to the 6th power). First of all, if I was using the prefixes, what would this be using a prefix to make it simple? Mega. Because I have 10 to the 6th right there, mega. So this would be 2.57 mega whatevers. Let's say it was joules, so that would be megajoules. How about if I wanted to write it out in straight joules without scientific notation? Then what would I do? Okay, so I'm just going to put a bunch of zeros here. And then I'll move the decimal 1, 2, 3, 4, 5, 6. I'll erase those two. And so that's my number if I were to write it out with zeros. It's really annoying. That's really what I do. I mean, I write them out and count them out. I don't like doing that. But you need to be able to go backward and forward between numbers. So on Moodle, you can go to, there's a link for practicing scientific notation. And you can go there and just practice and make sure you know how to do it right. So I recommend going there. I mean, if you do it, you do 3 of them, you get them all right, you might say, hey, I got this. If you do 3 of them and you got 1 of them right, you might want to keep practicing. All right. Here's the question. Suppose your cell has 5 megapixel camera, a 5 megapixel camera, your cell phone. Suppose I could learn to read. How many pixels does it have if it's a 5 megapixel camera? There we go. We got a first answer that was for somebody with a clicker. I see people raising their hands and telling me the answer correctly. Caleb's the only one who's going to... There we go. I only have one more person to answer here. Okay, I'm giving up on the last person. What we got here was one person said 500, 2 people said 5 million. Mega, capital M, is 10 to the 6, which means million. So the answer was 4 there, 5 million. Okay. And of course, at this point, you haven't memorized these. Special units, here we go. Getting back into... These are really I don't know what I was thinking. Let me just point out that I put these together really late at night, Sunday night. The last unit of distance that we have is the parsec, which stands for parallax second. It's actually parallax arc second. I didn't put arc in there. We'll learn where that comes from, but it is the biggest unit that we tend to use, and it's actually not very different from a light year. A parsec is 3.26 light years. But I mean, if you're into Star Trek, you've got to know what a parsec means. When I was a kid, I thought it was a made-up unit. I didn't know that it was actually a real unit used in astronomy. But Star Trek, for anyone who's looked at it, they actually were pretty good scientifically, making a lot of predictions of cool things. Like, you know, people say their little transponder things were pretty much our cell phones that we have today, our smartphones, and, you know, they had the photon torpedoes and that kind of stuff. They were pretty good. You can watch things on the physics of Star Trek. All right, another clicker question for the 4 of you. How far away from us is the sun? If you miss this, I will frown. What, we're doing it in sign language now?
Yeah.
You know, I understand that. When I was a kid, we got out the encyclopedia and learned sign language from the encyclopedia. Although, that's all I understand is A, B, C, D, E, F, G, and I'm really rusty. Just in case you start trying to test me.
Yeah, no, I don't even know the whole alphabet. I'm still the important.
Okay, so we had 4 people that said 1 astronomical unit, and they are right, because that's what the definition of an astronomical unit is. By the way, since you're probably wondering, who is this goofy dude who walked in? This is Reese Jimenez, who is our lab TA, and he will do a great job for us. Right, Reese? Right. Okay. Here is the website on the scale of things that I was referring to earlier. This picture here is trying to illustrate how big and small things can get using scientific notation. Hence the reason it came after the scientific notation part, but why was the scientific notation part so late? I don't know. And so we have the size of the proton here is very tiny, go up to, the height of a human. It says 1 meter. Gosh darn it, I'm pretty close to 2 meters, 1.89 meters.
This is me to China.
Not going to touch that.
Wow. This isn't being recorded, is it?
Yeah, of course it is. Okay, and then we go up to
For children.
the size of, yes, for children. There we go.
I'm going to cut that clip now.
The size of the visible universe is up here in the order of 10 to the 27 or so meters. So you can see the range here from around 10 to the minus 18 to 10 to the 27. That's a huge variation in size. So this website, htwins.net, is really, really cool. And we shall see now. Unless, of course, I fail. But I don't plan on failing. All right, there we go. So this is showing sizes of things. Now I'm going to start, this here is, 10 to the 0. We're talking about things like a meter or so. A human's about 2 meters. Beach balls are about half a meter or quarter of a meter. If you go smaller, we can zoom in and we see a shrew, a chicken, a hummingbird. I don't know what Russell's teapot is. We see microwaves. There you can see how big a microwave is compared to a coffee bean. About the same size, right? Keep zooming in. We can see how big a little droplet of sleet is, a grain of rice. They're about the same size. An ant, that sleet's going to crush the ant. Actually, something I learned when I was in Malaysia a few years ago, an entire colony of the smallest ants could live inside the head of the largest ant.
Wow.
Yeah. There's a pretty big range of sizes for ants, it turns out. I don't know what duckweed is. I do know what sunflower seed is, though, for the record. Okay, keep zooming in. Here we can see the width of a human hair, about half the thickness of a piece of paper.
Wait a minute. My hair is thicker than
Yeah,
this.
my hair is.
Yes, it varies by person. I have thin hair, okay? Good.
Thinning or just thin?
Both. Okay, truth. My sister and I are very similar. Her hair is thin like mine as well, which makes her also look like she's bald, or balding, which is really embarrassing for a girl. For me, I mean, I am balding, right? She's not. But like, if you look at this part of her head, it looks about the same as mine. It's pretty embarrassing for a girl, For a dude, you're like, yeah, I'm old. I should zoom out a little bit so we can see that dust mite clearly. You'd want to see the dust mite. The paramecium, human egg. Cruising on in, there's the size of a skin cell, a blood cell. Now we're into infrared light and a droplet of mist that makes a beautiful rainbow. Get down smaller and we've got E. coli, chromosomes, a particle of clay. You may not know this, but the difference in something like clay and sandstone is the size of the particles. Clay is smaller particles than sandstone. You think of them as very different because clay, you put water on, it's very slick, whereas sandstone's rough. It's just because clay has small particles. Okay, zoom in farther. This is awesome, I think. We see some viruses here, bacteriophage. There's the HIV virus in all its beauty. Now we're down to ultraviolet light wavelengths. The smallest size you can see with a visible telescope. You can use things like, or microscope, wow. Yep.
I would hope you could see stuff bigger than
Yeah,
that.
yep. Get down smaller. The porcine circovirus, I have no idea what that is, but I don't eat pork, so I'm probably safe. DNA, the double helix structure. Keep cruising down. Now we're getting down to the size of buckyballs and carbon nanotubes. See X-ray size now. Keep going down. We have the ever-famous water molecule, otherwise known as Mickey Mouse. And the carbon atom. Get down to a hydrogen atom and a helium atom. And Now we get down to gamma wavelengths. Now we're down to the size of a nucleus. The classical electron. Electrons are actually believed to be points. They have no size. But if they had a size, that's the size they would have. Okay. I know that sounds pretty weird, but so be it. The proton and neutron, tiny little things.
Do electrons exist in the third dimension if they're just points?
Well, when we talk dimensionality, we live in actually 4 dimensions. 3 of space, 1 of time. Anybody who's watched Twilight Zone knows, electrons, we believe, are just points. The end. Nothing extra dimensional about it. Now, it could be that, you talk about something like superstring theory that posits another, I think, 7 dimensions. Maybe there's something weird going on in those 7 dimensions that, that we don't know. Okay, we keep going down. The range of the weak force. The weak force is one of the 2 forces that are in action to hold things like protons and neutrons together in a nucleus. And so its range is very tiny, much smaller than the size of the proton even. And you keep going down and you have, hey, look, the up and down quark. Those are the biggest quarks. Quark is, by the way, a nonsense word made up by James Joyce in his book Finnegan's Wake. And Murray Gell-Mann adopted that word to describe these little particles that we believe protons and neutrons are made of. So up and down is what protons and neutrons are made of. You have the strange quark, which was called strange because they found some particles that had a strange behavior. They theorized there should have been a 4th one, but they couldn't find it, so they called it the charm quark. They said it's living a charmed life, and that's why we can't find it. Then they determined there must be 2 more, so they named the last 2 the bottom quark, and we'll see coming up here the top quark. And we are at really, really tiny sizes now. Notice over here we're at 10 to the minus 22. And we go down to the size of a neutrino, measured in yoctometers, 10 to the minus 24. And, we're pretty much done at this point. There's nothing inside here if we go down even further. We have a theoretical Planck length, but it's not something. Okay, now let's go bigger. So we're back to human-like sizes. Well, we're getting there. Human-like sizes, we zoom out. Okay, we got the size of an average American home with a good room, a teeny garage, bad room. He was having fun. Yes, football field, Eiffel Tower. We should zoom right in there on the Half Dome. Awesome place. Hoover Dam. You can tell this is dated because right now, Hoover Dam has a dam right across, or not a dam, but a bridge across over here. So you no longer drive across the dam. It does make it a lot quicker to get from Vegas to, other places if you're going that route. But I kind of like driving across the dam. I've taken the dam tour twice. And yes, they call it the dam tour and they make a big deal out of it. Everybody thinks it's such a funny joke. I took the damn tour. You can get the bumper sticker. Well, then you have to go take the tour. Uluru, we tend to be Seventh-day Adventists here. And if you know anything about the Adventists in Australia, you know about Ayers Rock. Uluru is Ayers Rock. It's kind of been renamed to go to the native people's tongue, and that's where the whole "dingo ate my baby" occurred. The Chamberlains, Michael Chamberlain, their baby was taken by a dingo, and nobody believed that a dingo, a wild Aboriginal dog, would take a human, and so she was convicted of killing her baby. And then it was overturned eventually. It was a big story. They made a movie called A Cry in the Dark. And everybody jokes about, dingo ate my baby. Here we have Mount Everest, the tallest mountain in elevation, not the tallest mountain on Earth, but the highest elevation on Earth. Tallest mountain is in Hawaii. It's Mauna Kea or Mauna Loa, and I can never remember which.
It's the Hadron Collider? Oh, yeah.
Yeah, here, Hadron, but the Large Hadron Collider there in, well, Geneva area. You see here that Halley's Comet, and yes, it's not Halley. Bill Haley and the Comets was a band, and it was at that point when people started mispronouncing Halley's Comet. At least that's what I've read. But the dude's name was Halley. So Halley's Comet, you can see, is about the size of Mount Everest. Not that big, really. Keep going out. I don't know what Palm Jebel Ali is at all.
Dubai.
It's interesting to note that Phobos here is smaller than Rhode Island, and so is a neutron star. A neutron star has a mass that's like, 3 times the mass of our sun, and it's smaller than Rhode Island. It's very, very dense. It's the same density as a nucleus. Phobos is one of the moons of Mars. So is Deimos. Deimos and Phobos are the moons of Mars. They are fear and terror. Nix, Hydra, Dysnomia, these are... actually, somehow I thought Dysnomia was an asteroid, but I could be wrong. It could be a moon as well. Keep moving out. We have here... Quaoar, I don't think, has been categorized as a dwarf planet. It's just a really large Kuiper Belt object. These are dwarf planets. A lot of moons here. Now we're getting to some planet sizes. Sirius B is a star. Now we're seeing all stars.
Wait, go back to Minecraft World?
I don't know anything about Minecraft World.
Yeah, Minecraft World.
Where do you see Minecraft World? Oh, there it is.
Minecraft.
Is that as big as it's supposed to?
I don't know anything about Minecraft. I know my son spends a lot of time playing it, but...
Can I? I wonder what that's supposed to mean.
I don't play Minecraft. I don't know.
I guess if you
Here you see Alpha and
I thought it was a sand.
Alpha Centauri A and B. It's a double star. And Sirius A, it's also part of a double with Sirius B. Getting to big stars, Arcturus, Polaris, the North Star. Aldebaran, getting even bigger, Deneb. These are big stars now. VY Canis Majoris is the largest known star. But then even larger than that is our solar system. Our solar system is larger than the largest star. And we're now getting to ridiculous sizes. Some nebulae. The Oort cloud is actually the largest extent of our Milky Way galaxy, where we have stuff. So this is, if you want to say everything in the Milky Way galaxy, you'd say that size. The pillars of creation is very interesting. We'll learn about it later. It's called pillars of creation because you see active star formation there. Eagle Nebula is what the pillars of creation is in. Get bigger and bigger. The Sombrero Galaxy, which is really a pretty galaxy to look at. It looks like a sombrero. The Milky Way galaxy is large. The Andromeda Galaxy is believed to be a little bit larger, but it's when you see pictures of galaxies that are supposed, if it's actually a picture to look like the Milky Way galaxy, it's probably the Andromeda Galaxy because it's close. We take pictures of it, and we believe that we look a lot like it. And then we have some bigger galaxies here. We have our local group, the Virgo Cluster. Keep going out. The Sloan Great Wall, which was the largest thing known to science until very recently. And the observable universe. So it's a really cool website, right? And of course, you can go there. I gave you the link. What was that?
What's the website name?
It's right here, twins.net/scale2. And going back to I wonder if it stopped recording because I was away so long. We'll see. All right, going back to these pretty slides. I tried to run that on my tablet, but it's using flash. Tablet doesn't run flash. The things that everything in life is made of, protons and neutrons. Protons are positively charged. Neutrons are neutral. Then we have electrons that orbit around them. We'll have to learn more about those because the production of light is tied into the behavior of atoms. And you've just seen things about the size, so I'm not going to go into the size there. In nature, physicists have determined that there are only 4 fundamental forces. Those 4 fundamental forces, the weakest one is gravity. But gravity is the one that really is the most important to us in astronomy, I think. Because in the end, gravity is the one that has the biggest effect over large distances. Gravity is attractive between all masses. And so as you get more and more matter, you have a stronger and stronger force pulling things together. The next weakest force, it depends on the range you're looking at, but the next weakest force is the weak force, a force that acts between protons and neutrons holding them together. You go up in strength, you have the electromagnetic force. That's the force that holds an electron to the nucleus of an atom. And then you go to the strongest force, which is called the strong force, another force that acts only in holding protons together and holding quarks together. So those are all the forces we know of. And you notice the ranges. The weak force, 10 to the minus 18 meters. The strong force, 10 to the minus 15 meters. They're very, very short-ranged forces. The gravitational electromagnetic forces are infinite in range, but charge tends to be equal. You have as much positive charge as you do negative charge. And because you have that equalization in charge, the electromagnetic force becomes very small when you get bigger because you're just getting closer and closer to neutral. But because the gravitational force is always attractive, it gets stronger and stronger as you get bigger and bigger. So in the end, the reason that the moon orbits around the Earth, the reason the Earth orbits around the sun, the reason the sun orbits around the center of the Milky Way galaxy, the reason the Milky Way galaxy interacts with the other galaxies, all of this is because of the gravitational force. The gravitational force is also the reason that we have gas that collapses down to form planets.
So it's so much information. It's
Yeah.
So much.
Well, yeah, we are getting an overview of we're getting an overview of things we're going to talk about. So nothing here is like that's the end. You should have it all learned. But gravity is ultimately the winner. When you have something like a star dying, it dies because gravity finally won. And black holes form because of how strong gravity is. It's our ultimate force, I believe, in astronomy. Now we're almost to the end. Elementary particles, the protons and neutrons themselves are made up of those quarks and ups and downs exclusively. So a proton has 2 ups and a down. You notice the colors are different? Quantum chromodynamics says that we have to have quarks in 3 different colors. And to make a hadron, to make a baryon, such as a proton, you have to have 3 quarks all with different colors. What does the color mean? Nothing except for that quarks have 3 types of charges. And so they call one of the charges blue, one of the charges red, and one of the charges green. They chose the colors because we have 3 primary colors. That is, we have 3 kinds of cones in our eye. One cone sees blue light the best, one sees green the best, one sees red the best. So we have the 3 primary colors of light, red, green, and blue. They say, hey, there's 3 primary colors. There are 3 charges for the quarks. Boom. So a proton is up, up, down. A neutron is an up, down, down. And you don't even need to know what they're made of. Just, we have, even protons and neutrons are made of smaller particles. Okay, and this is going to be our last clicker question. Whoops, got to get to the right place. Don't answer yet. I'm not there. Okay, this is our last clicker question right here. You can answer now. Which force is the most important to astronomy? Sorry, Reese, I know. I told you to come 15 minutes. You did check in, right?
Yeah.
Okay. He's getting paid for this. All right, that's only 2. with only 4 people, I feel stupid waiting for answers. Okay, there we go. We're all in, and everybody said gravitational force. Yeah. Good job, folks. You're getting the important things that are actually, what I want you to learn from this. Now we're going to have just like these 4 brief slides on observing the sky. Then we're going to go out. You can see it's dark out now. It's dark enough that we'll be able to see things in the sky. When you look at the sky, we have constellations that are very interesting. The best way to enjoy astronomy is to go out there and look at them, which is why we're going to do that. We have a picture here of the southern sky as it looks now. So you have Scorpius here. My astrological sign is Scorpius. Historically, that meant that the sun was in this constellation when I was born. That is, if you were to be on Earth and look at the sky during the daytime and figure out where the sun is with respect to the stars, it was in the constellation Scorpius. Only one problem. I was born after the 1700s. And they changed the calendar. They changed the calendar by, depending on where you were, 10 or 11 days. So you went to bed one day and you woke up 11 days later. It's pretty awesome when you think about it. And because astrology is hocus pocus, it's what we call a pseudoscience. They pretend to be scientific. They use scientific information, but then they tie it to something that has no scientific basis. Remember, a hypothesis had to be based on scientific ideas. Astrology isn't based on scientific ideas. It uses science, but it's not based on scientific ideas. And so since it's hocus pocus, they decide, hey, why do we need to be accurate? It doesn't mean anything anyway. And so when I was born, the sun was actually here in the middle of Libra. But hey, who cares? So we have these constellations. It's kind of funny. You can't look at a lot of astronomy websites because the signs of the zodiac are blocked by Union College's, our filter. And so it's like, oh, you were looking at Sagittarius? That must have been looking for your horoscope. No, just looking at the signs of the zodiac. The constellations on the zodiac. The zodiac means the zoo. And the signs of the zodiac are the constellations that fall on the path that the Earth takes as it goes around the sun. So that's how they get those signs of the zodiac. So looking in the southern sky, I believe I'm going to be focusing on the southern sky. Is that right? Yep. So we're going to be looking at Sagittarius. We can only see Sagittarius, Scorpius, Capricorn. Well, I'm going to look at these ones specifically. I'm probably not going to look at Libra or Capricornus or Ophiuchus or Serpens. But we're going to look at these 2. We can only see those pretty much for the next month or so. After that, they're going to be below the horizon. But I want us to learn these things now because, well, number 1, it's kind of fun to see Scorpius. And number 2, the center of the Milky Way galaxy is right about there. Sagittarius, which you would never know by looking at this picture, is an archer it's a centaur archer, I believe. We draw this little picture like a teapot. That little teapot is not a centaur archer, so that would actually count as an asterism, except for it won't be in the sky when you do your star quiz. The center of the Milky Way galaxy is like you're pouring something out of the spout of this little teapot that they draw for Sagittarius, right there. I want everybody to know where the center of the Milky Way galaxy is. That's why we're going to spend some time learning that right now. And then we'll be spending a lot of time looking at things in this region. Those are things that you're going to see a lot more of and that are a lot easier to identify. So we're going to go out there and we're going to look at things. Now, when you're looking, you don't see just these stars, and you certainly don't see those lines connecting them. You have to see those in your head. How do you get that? Well, practice looking at them, identifying them, getting used to them. Now, this is looking south. If you look north, you're going to see what we call circumpolar constellations. Circumpolar because they're going around the North Star and never set at our location. And so no matter what time of year you look, you're always going to be able to see, well, not the Pleiades, but you'll be able to see Perseus and Andromeda and Cepheus and, the things here. We have Draco. Draco who's attacking. Who's Draco attacking? Hercules. So Hercules is right here. I recognize Hercules because of his chest there. And so that's what Reese is going to be pointing out primarily. Many of these constellations have interesting stories that go along with them. So either Reese or I will at some point probably tell you about the story of Cepheus and his wife Cassiopeia and how they chained Andromeda to a rock, and then good old Perseus, who had just slain Medusa, comes by and sees this naked chick tied to a rock, and the parents spying to see what's going to happen to her, and he comes and talks to them and negotiates into getting her as his bride. It's interesting little stories that go with these. So it's kind of fun to learn some of that mythology. Something also that you need to be aware of is there are multiple mythologies for some of these stories, some of these constellations. And these constellations are not the only way of naming and choosing constellations. American Indians, for instance, had different names and constellations. We now have 88 total constellations that cover the sky, and we'll learn a lot more about the constellations in class. Going out there, we're going to spend our time identifying where they are, and we'll want to try to learn the rough areas for the constellations. Next to last slide. The first thing you need to do when you're going out to look at the sky is to get yourself oriented. Once you can find, okay, I know what that is, then you can start to using your understanding of the relative positions to help you identify where other things are. And so while the North Star may not be the brightest star in the sky, it's a good one to use to orient yourself. Now, when we go out there, how are they going to find the North Star?
Depends on,
When we're out at the dam.
well, pretty much the path runs north. So all you got to do is go straight.
Yeah, just look down the path and look up and, hey, look, there's the North Star. But when you're not out there at Holmes Lake, the easy way to do it is to find the Big Dipper and then just take Merak and Doobie, and they almost point straight to Polaris. And so if you find the two stars at the end of the cup of the Big Dipper, you can find them pointing up to Polaris. Now notice here that the Big Dipper has a cup that's pretty big. The Little Dipper has a cup that's pretty small, and it looks like the Little Dipper is pouring into the Big Dipper. Also, you'll notice that the handles are going opposite directions compared to the dippers. No big deal. They're just different kinds of dippers. When you look at the Big Dipper, these Big Dipper stars are all pretty bright. It's easy to find the Big Dipper. The Little Dipper, which stars are they going to see?
Well, you'll see Polaris, and then you'll see the two ends.
Yeah, that's all you're going to find. The others are really, really faint. Once you find those two, you can start identifying the others. But you're not going to look up there and find the others first. So finding the Little Dipper is harder because you have fainter stars. The Little Dipper and Big Dipper are both asterisms. There are constellations associated with them. One constellation that's shaped roughly like this is Ursa Minor, the small bear. Never mind about bears and tails. These bears have tails. This one here, the Big Dipper, is shaped something like that. You notice Ursa Major, by the way, is the name of this. I said the Big Dipper. The Big Dipper is part of Ursa Major, but Ursa Major is far bigger than the Big Dipper, whereas Ursa Minor is virtually the same thing as the Little Dipper. When it comes to the lab final, you can count both Ursa Minor and the Little Dipper, but you have to know the difference. You have to know Ursa Minor is this area that's just barely covering the Little Dipper. You have to know Ursa Major goes all the way down here, comes out, comes up here, and comes back. Right? You can't just say, oh, there's the Big Dipper and Ursa Major. We will not give you credit for that. You have to know the difference. And another thing that's easy to find once you found the Big Dipper, you follow the arc of the handle, and it brings you to Arcturus. We're very funny with our mnemonics. Arcturus we'll be able to see now. When it gets time for the star quiz, we won't be able to see it because the the sky appears to rotate. That is, if you go outside right now, when we go out there, I'll have you look up overhead and see what stars are overhead and see what stars are on the western horizon. And then when we leave, I'll have you compare again, and you'll see they've all moved. The ones that were on the western horizon will have set. The ones that were overhead will have moved a measurable amount because the Earth is rotating. And over time, what we see overhead is going to change. That is like at 8 p.m. tonight, what you see overhead is not the same as what will be overhead at 8 p.m. in a month because of the Earth orbiting around the sun. So, and this is the last slide. The stars move from east to west throughout the night. The end. Okay, we are now, let's go here, stop the recording.